Hi. Some weeks ago, I was ready to start working on problem 4. And while studying the section, I made an example where I computed K3 for a certain K3 plus for a certain curve, and found out that its index over the rational numbers was 8. And I concluded that the index of K3 over, or the order of K3 over K3 plus was 4. And when I came to that conclusion, I realized that it would be intractable, or believed it would be intractable, so I stopped having identified K3 plus. Now, when I read problem 4 before starting recording, I realized that that means that either K3 equals K3 plus, or it's at most of order 2 above it. So that means that I had made a mistake while computing my example. So what I wanted to do was to revisit the example and get everything right. That turned out to take a while. So what I'll do here is to show this work. So this is a presentation of my work. Now, the curve we are working on is very simple. And I've depicted it here. And we have the points, the real points of order 3 here, the inflection points on the curve. So I did it in Maple, this part of it. And here's the plot I showed you. So the first thing was to find the points of order 3, or the equation of it, and that's the equation. Let's make it a little larger. That's the equation I showed you on the PowerPoint presentation. And then I listed all the points of exact order 3. Actually, I got the unit in this list as well. So you saw I computed omega 1 and omega 2 by the integral. So it's just to get a numeric value for it. And always these consistency checks. So by using the Weierstrass elliptic function and its derivative, we find the points. This of course means that it's purely imaginary. And so that's the list of points. So I solved the second order differential equation, the square, or the fourth order, so this x squared gives this. So that means that K3 plus must contain square root 3. So we define the two x values, and then the opposite ones will occur as well, of course. And it appeared to me that square root minus 1 had to lie in K3 plus as well. And an argument for it is to multiply the square of the two solutions here. So this squared. That gives minus 3 divided by 36. So that means the square root of minus 3 must lie in K3 plus, as well as the square root of 3. So this is one way. Well, we should start with this field and then just extend it with one of the square roots here. So we just need to see that this square root doesn't lie in this field already. That's easy to see, but it does require some work. So what I did was that I wrote it an element in the field, and then where A, B, C, D are rational. Oh, it just occurs to me that this might be a too complicated way to do it. So let's instead, oh, that was too far, have A plus B square root 3, where A point B are fractional Gaussian integers. Oops. That may be much more easy. And this should give one-fourth, and 2AB should be 1/6. So that means AB equals 1/12. So if we multiply this by 144b squared, divided by 4, that's 36. Then this gives unity. So we just need to compute the discriminant to see whether such a B exists. 36 squared that's 1296 minus 4 or 12 times 144. I'll just do it the 8 plus 4, 2 plus 4, 6 plus 1, that's 7, 728. So we subtract 3, that's 400, and add 32. So is that a Gaussian square? So we can divide it by 16, I think. Let's just do it 4 at a time. Oh, it's just a factor of 4, yeah. That's 54, that's 27. So it boils down to whether 3 or not is a Gaussian, is a square in the Gaussian fractions, and it's not. It's actually a prime. So it's easy to see, of course, but it does require some work. And that's usually when we say something is easy to see, it's routine work, and it can be done more or less complicated. Maybe the way I did it, I prepared to do it, is indeed more simple, but I like this way better in a way. Well, we'll see. This takes more arithmetic, but and this one requires a little more thinking, maybe. All right. So this is K3 plus. And now we have made a quadratic extension, and a quadratic extension. So it's not difficult. Oh, and here we have the points, by the way. The ones I derived from on the Maple sheet. I realized not so difficult to understand the values. Here we go out to his omega 1. So going out here, it's real, and it's decreasing the Weierstrass P function, so the derivative is negative, and this, of course, mirrored. And up here, along the imaginary axis, we have only even numbers in the power expansion of the elliptic Weierstrass function. So it gives a negative guy, and since it goes from minus infinity towards minus 1/2 up here, like here it will have the value 1/2. That's these points. And so it's easy to see. Now this is a little more difficult, but here we are on the line. The imaginary and real parts are equal, so the angle is, I say, 45 degrees, and since only even powers occur in the Weierstrass P function, we get adding imaginary terms, so it will be an imaginary number. So it's actually possible to reason these values, not just rationalize them. Now, so I believed it was the simple abelian group, but you see the Galois group here is actually permuting the x values. So that means that it is a subgroup of the symmetric group of order 24. And since it's an extension of 8th degree over the rational numbers, we get here the Silo 2 subgroups of order 4. So that's known to be the dihedral group of order 4. So I realized that at this point I didn't know the Galois or the automorphisms of the field. Now, that was a challenge. And this was my first work in many years with Galois theory, so I felt quite insecure. But what I did was, let's hope that it can be written as an extension of Q of the Gaussian integers, or the fraction field of the Gaussian integers, because that contains a fourth root of unity. And in that case, the K3 plus, it can be generated by a fourth root. And one way to find it is to find an element whose fourth of K3 plus, whose fourth power lies in the Gaussian fractions. Now, there was no indication in my book on field extensions and Galois theory how to do that, so I did it the hard way. It's called the Lagrange resolvent of this extension with respect to, I don't know why, I've forgotten what that means. So I started the hard way to expand this, and that was intractable. So instead, I did it symbolically, x being the square root of 3, and y being the square root of 3 plus 2 square root 3. So using these relations, it simplifies this expansion we saw before. And then we can find the constant term by assigning x and y to naught, and subtracting it, dividing by x, and simplifying, setting y to naught, and the same thing with x. We get the coefficients of x and y, and finally the coefficient to xy. They needed to vanish. So we just solved the equation that, actually this is an ideal we are working on, but never mind. So we solved the equations that all this vanish. And I didn't believe that it was possible. And when I saw that, my heart sank a bit. Oh my God. Will there be any sensible solutions here? Oops. Oh, naught, of course, naught's a solution. That's silly. And another one with square root minus 3. Then there was one here. There was actually two. AB vanishes and C equals minus 3D. AB vanishing, C equals minus D. So let's see what happens when A and B vanish. So we set A and B to naught, and then the equation for x becomes this. The equation for y and xy is already zeros. Good. Now this is a homogeneous polynomial in C and D, which of course explains why we get these solutions. So I solve the polynomial and get the four solutions, minus 3 and minus 1. And then we can see of what should we take the fourth root. It turns out to be 12 or 108. I opt for 12. So I put it into the expansion here, and it does indeed give 12. That was really a miracle. I really didn't expect it until I saw it. And if we take the square of this guy, then we get 2 square root 3. How could that be? Actually, it's not so unusual a phenomena, but it was really a revelation to me that it was possible. So now we've found an element. Oh, this is the element to extend the Gauss fractions. And here we have it. And then the theory simply says that the isometry, the automorphism, that's wrong, isometry is wrong. The automorphism is the imaginary unit, that's the unit, the fourth unit here, times t. Well, that's one of them. One could use the opposite one as well. But now, we opt for this one. Now, the first thing is that t squared is 2 square root 3. So sigma operating on t squared gives minus t times minus t. That's minus t squared. So that means that sigma of square root 3 is minus 3. And we can find sigma of this part. What we have to do is isolate it and then use sigma on each part of its own. This gives minus square root 3 minus 1. And 1 divided by minus... then we have to substitute what t is. That's square root 3 minus 1 divided by 1 plus square root 3. We must do that. That's here. So we extend by the numerator. That gives square root 3 minus 1 squared. So that's 3 plus 1 minus 2 square root 3 divided by 3 minus 1. So that's 2 square root 3. That's what it says here, 2 minus square root 3. And then this. So we need to, that must be the other one I prepared we should do. There's an I up here. Well, why did I put that up there? Oh, it's here. Never mind. We'll just leave it. So we do the same trick. And the content gives 12 minus 9, that's 3. So that means that... Now, does that make sense? This I is totally irrelevant. So that's what we get, and that's what I use here. Let's just check that it's times plus gives minus. Oh no, that's true, this is smaller than 1, so it had to be this, and minus I is just there. Now, sigma squared on this. Oh, we just applied here. Sigma squared on t gives minus t. Sigma squared on this gives the same. And sigma squared of this is sigma squared of this. So it just changes sign. So it just follows from this guy. And then we can apply sigma once again here to end up having sigma here and results in this. And finally, we are able to find the value of x1 and x2. defined here. It's square root 3 times this guy. This changes sign, and this. So we see its rotation clockwise 90 degrees, so it has order 4. That was the end. Right. So a positive ID that it is that the Galois group is the dihedral group of order 4. The dihedral group is defined by the two equations 2 and 3. Actually, I don't like to say defined. It's represented by it. I'm having some problems with defining groups by the relations. I think it's very good to have the idea that we construct all finite words of the letters sigma and c, and then using adding the empty word and using concatenation as the operation, and sigma to the fourth and c to the second gives the empty, is equal to the empty. It's clear that we have a group. It's easy to, if you concatenate sigma with sigma to the third, you get the empty one, so it's obviously a group. But next, if you impose this condition, formula 3, the quotient, if that's a group, then we need the group generated by this element to be a normal subgroup, and it is not. So to do it, we have to find the normal closure in this semi-free group. And I don't know how to do that. So to me, it's. I also believe that there are some problems with the algorithms for identifying groups with this. But never mind. It's a useful way of identifying groups, so I'll accept it as that. Now, of course, this we already know, and then computing this, it gives t, and can we conclude this from that? No, I think we need to operate on square root of minus 1 as well. Square root of minus 1 does nothing, change sign, does nothing, change sign. So with these two, I think we can conclude this. And these two equations characterize the dihedral group, so that's a positive ID. So now, I was aware of this. Now I wanted to include the second coordinate of the points of order 3. So computing the function gives this. I didn't do that by hand, I just let Mabel do that. So we get the fourth root here and the fourth root here, and I believe them to be incommensurable over K3 plus. That is, the fraction doesn't lie in K3 plus. That is actually true. But then later when I did it, I included the imaginary unit here. And then it suddenly turned out that they were indeed lying in the, or that this guy lied in K3 plus extended by this guy. So there we go. And that was, of course, where I thought it was the fourth order extension, so that was just too much. Actually, we know that it's a subgroup of the general linear group 2.3. That means two-dimensional of set modulo 3z. And it's known to contain 48 elements. I knew that, but I didn't know the group. So I didn't study it very thoroughly. I was just interested in the order, of course, was 48. That's important. That's 16 times 3. So you see, this is impossible. It has to be at most 16, and it has to be 16, of course. And that means that the Galois group of K3 over Q is isomorphic to the silo or two-silo group of yield 2.3. So that's why we needed it. So let's see what they are. Group properties, subgroups, here we go. Subgroups of order 16, isomorphic to the semi-dihedral group SD16, semi-dihedral group XD16. Now what's that for a guy? So that's represented by these relations. The dihedral has this equals to a minus fourth, or a to the seventh, a to the third. My dear. Or rather, oh dear. So that's what I've put here. Let's go out. So now, can I actually see that this guy is contained in this extension of K3 plus? So I did what I've done a few times before, but this time I included the imaginary unit for reasons I don't really know why. I was tired when I did it, so you already have this. And you see, if you have been working with number theory, then the integers extended with square root 3, they have a unit square root 3 minus 1, and this is actually a square of that unit. Oh, there's a factor 2 as well, okay. So we can write it as 1/2 times square root 3 minus 1 squared. That's what we do here. And then 1/2 was, I didn't believe square root 2 would line this. I really didn't. But this guy does. We extend by 2, and then this is a Gaussian square. That's 1 plus y squared. 1 plus I squared. So that means if we define y1 like being this guy divided by 3 in the, and then under the square root, and then y2 by multiplying by the positive guy here. Actually, I want y1 to map to I2, so we have x1 maps to x2, so we have to go up to our points here and see we have x1 here. This guy maps to x2, which is here and here. So we have to choose one of these points. And since it's a quadratic extension, we can choose any point. Now, I choose this one, so we do a simple operation. I had some idea we might be going round, of course. So that's why I chose this value of the second coordinate. There we go. And that implies that y2 squared equals this times y1 squared. And then we need to see how can we extend. Well, we have two guys to extend. We have the complex conjugation, but we do that, we choose the natural one, which is embedding K3 in the complex numbers, and then just use complex conjugation. So I don't write that, but we have to extend sigma. And we have extended, well, we have to work out what it becomes, and we'll get a choice, of course. But sigma squared, and there we use this value for sigma, which we already have, minus I. If you don't remember, I'll just go up to it. Here we have it, minus I times the minus. Now I'll see if I can go back again. Here we are. And then the relation we just found, I'm using. And then we use the formula for I1. That's this divided by 3 squared, y1 squared. So this is what is left. This gives minus I halves, and that's just y2 squared. So that means we may extend sigma by assigning sigma of y1 to be y2. And next we need to see then what happens to y2. And that's a trivial guy, square root 3 changes sign. We use the definition of y2 here. This is constant, this is minus square root 3 minus 1, and y1 maps to y2. And then we insert y2, and that's this guy, and then we simplify, and then the phone's ringing, so we'll just make a break. So I'm back again. Now we should look at the whole action. I believe we finished this slide. So to find the GL23 representation, we first, or even to identify the group, we first see how sigma maps the y values, y1 to y2, y2 to iy1, which then goes to iy2, iy2 goes to -1, minus i1, which goes to minus i2, which goes to minus iy1, which goes to minus i, which goes back. So it has order 8. And that means that our extension of sigma actually introduces changing sign. That's something I find it hard to understand that it happens, but it's obviously necessary that it happens. Well, and next we to find the representation, we need to see where these 2 points map. So first 3 omega 1. Omega 1, that's this point, x1 minus y1. So minus y1, that's to minus now x1 goes to x2, that's this guy, and minus i1 goes to minus i2. This was i2, so this is the guy, so it goes to 1.1. Oh, that's where we are, 1.1. So that's 1.1, and that gives the m sigma this 1, 1. And then 3 omega, or a third omega 2. That's minus x1 I y1. Minus x1 goes to minus x2. So that's these 2 guys that come into play. And this is I y1 goes to I y2. So this one multiplied by I gives -1, gives this guy. So it's -1.1. -1.1. So now, of course, we have c squared is identity, and sigma to the 8th is the identity. So we just compute c sigma c, and when it operates on the imaginary unit, it gives the imaginary unit itself, and y1 is by c mapped to y1, mapped to y2, mapped to minus y2. No, is it not? Mapped to y2 and y2. Oh yeah, that's a complicated guy. C gives to I y2. And I y2, that's c to the 3rd of y1. So I think these 2 examples are sufficient to show that c sigma c equals sigma to the 3rd. So that should give us a positive identification of the semi-dihedral group of order 16. Oh! Now, this representation I put into Mabel. Here we've got them. And b to the various powers. We see here we end with -1, or have -1, and here we have the unity, the unit matrix. And ABA is, of course, the third guy. So that finishes my example. So now, and only now, do I feel ready to start explaining, doing this problem, explaining why it has to be like that. So I've really been down in the machine room doing the actual computations, which was challenging. I learned a lot doing it. But here we have to take another view of it and realize why it has to be that from more general terms. So now it's time to lunch, and I am finally ready to start working on problem 4. We have the addition formula 7.1, where m is the slope between the 2 points. When we have the points of some order, there will always be some with different first coordinates. So let's add them and see what happens. That's my idea for this problem. So when we operate with sigma, then the first coordinates, all of them, are mapped to themselves, whereas the y values may change sign. As I see it, then the exercise here is to show that they either all remain the same or all change sign. So let's try to operate on this equation with sigma. Then m squared must be the same, which means that sigma y2 minus sigma y1 equals plus minus, yeah. So let's take the 2 possibilities, there are 4 possibilities. One is that sigma y1 equals y1, and the plus sign and the minus sign O. So if this is minus y1, then minus, if sigma y2 is minus y2, then y1 must vanish. We have to do it the other way around. That may be possible, of course, if it's afforded to. We know that it's either plus or minus y2, So we have either y2 equals this, so it's A, which gives y1 equals y2. So they must map the same way. Or sigma, which is minus y1, minus y2, in which case y1 is naught. And then the change of sign of y1 is arbitrary. It can be the same as y2. All right. And then if sigma of y1 equals y1, no, minus y1, the opposite of, so 1, 2, it'll probably just be the same, but we have to go through the motions. Plus y1 equals y2 minus y1. And then A, if it's plus I2, then y1 equals minus, nonsense. I'm losing my concentration. y1 is naught, and then the sign is arbitrary. And if it's minus y2, then they are identical. No, then I want, oh, that's strange. We of course have to have the same right side. Then y1 equals y2. So of course they transform the same way. And if it's minus, then minus y2 plus y1 equals y2 minus y1. So I'm thinking in a very strange way, because I have to conclude that sigma of y2 equals plus minus or having the same sign. So I'm doing it in a very complicated way. So I'd rather start all over again. So first, if sigma of y1 equals 1, then we have to show that sigma of y2 equals y2. So assume, to prove the contrary, that sigma of y2 equals minus y2. Then we have minus y2 minus y1 equals plus minus y2 minus y1. So using the plus, then we get minus y2 equals naught. And in case of minus, the y2 cancels and we get y1 vanishes. So in either case, the sign of one of them is irrelevant. And now it should be the same. We assume that sigma of y1 equals minus I2 and assume minus 1. Minus I1 and assume, to prove the contrary, that sigma of y2 equals y2. y2 was y2 plus y1 equals plus minus. I'm using this formula again. Plus minus y2 minus y1. So the plus yields y1 vanishes and the minus means that y2 vanishes. So when the second coordinate is distinct from 0, naught, then they have to change sign the same way in order for the addition formula to vanish. So that means that sigma of a second coordinate for all of the coordinates change sign the same way, plus or minus. If it's plus, then all the second coordinates must lie in kn plus, so the extension is trivial. And if it's minus, then the extension is quadratic and they all change sign. And then we have to look at the points to get into the GL2N representation. And when x is constant and y changes sign, then when we look at the Weierstrass functions, then the Weierstrass elliptic function is even and its derivative is odd. So that just means that we change sign on the x value it comes from. And that means that the matrix associated with it is minus 1 point minus 1. And we saw that in the example I made as well. And then I believe the rest here is trivial. Now, what is the analogous situation for cyclotomic fields? Oops. So let's say we have a field F. Now, that's actually an extension of the rational numbers by an nth root of unity. So of course it's, I forgot the name of these polynomials, cyclotomic polynomials, I guess it is. And then we have maps from Ti. Each of these values map to a point on the unit circle, and there are two. No, it's actually a point. It's actually a point on the circle all of these lies. So we are in the complex plane generally. So we embed this in the complex plane. So the first coordinates I need to have some examples to see what's cooking here. So let's take order 3, where we have omega. So that's the 3 points. And there, of course, in this case, it's actually a complex conjugation that we are talking about. So mirroring of the second coordinates, that's the complex conjugation, which we always have. So the situation is the same. Now, what did I have to do with this? What is the analogous situation for cyclotomic fields? Yeah, I think the answer is that's complex conjugation. Right.